So our next speaker is Himadri Barman. He is from Hangzhou in China. That's where he's based, and he will tell us a tale about two kinds of exceptional points in the hydrogen molecule. So when you're ready, go ahead, Himadri.
Okay, thanks, Andreas, for inviting me for this talk. And hope I'm audible enough. So, as is mentioned, that I'll talk about two kinds of exceptional point, and in a very simple model, which I call this hydrogen molecule, and I'll tell more about it. But before I begin, I just tell there's another co-author who is a very young student, and somehow he came across to me, and then we started with a very simple project. And then he was doing his bachelor, so he didn't have much advanced knowledge about this PT symmetry or non-Hermitian physics. Just we started with simple model Hamiltonian, then we are just playing with, and it evolved that we could discover some kind of rich physics, and that is what I'm going to talk about today. And he's from this beautiful IIT Madras campus in India, where you can see spotted deer in the campus. And I am also not I'm also quite new in this community. So I was in this I attended, I think, in 2019 in Sanya in in China, and this was me. You can see me clearly, and this was my campus in Hangzhou. So you can see Mao Zedong there. Okay, let's come to the topic. So the brief outline is that I'll talk about something very simple Hamiltonian, which is two-level system, which probably everybody knows. And then I'll talk about the hydrogen molecule. Then I'll introduce non-hermiticity in this hydrogen molecule, and then I'll I'll add interaction to this molecule, because any molecule has interaction. So, well, interaction, the kind of interaction I'll introduce, that is also very simple and very well known in condensed matter community, which is called the Hubbard interaction. Okay, then I'll talk about the what kind of exceptional points we see there, and can we differentiate the different kinds of exceptional points in those in that kind of Hamiltonian. Then I'll just try to summarize or talk about the outcome. Okay, so let's start with this two-level system. Two-level system is just nothing like there are two energy levels, and then this become very interesting or popular when people talked about this avoided level crossing problem. What happens that if we add some kind of mixing term or this hybridization term, which comes in the means tries to, so the two-level systems are separated to energy levels, and there could be another term which is like cross term, the off diagonal term in that Hamiltonian. Then there's a probability of mixing that term, and also there could be some parameter that actually try to means this energy levels could be dependent on some parameter where this two level could be degenerate. However, because of this finite mixing term, you can see, so when this T is small, then the energy levels can meet tend to meet to a point, so it can be degenerate. But when T is large, then they are separated. So that is the avoided level crossing problem. And I just can't see what I there in the slides. So so the eigenenergies can be easily deduced, and it has this kind of forms. I'll just come to there. So I just mentioned this. So this was our two-level system, which was Hermitian Hamiltonian. So what our goal is that what our goal would be that make this Hamiltonian non-Hermitian. So very simple, that we can make it non-Hermitian in two ways. One is that adding non-hermiticity in the diagonal part. So this is the Hamiltonian looks like when it's non-hermiticity introduced in the diagonal part, and also we can make it non-Hermitian from the off diagonal part. We just make it asymmetric there, and in the diagonal part we make it add some complex term there with conjugate partners. So both has the similar kind of characteristic equations, and both give eigen energies, has a very similar form. And we can see that there's a term which is there's a discriminant in the, so there's a square root term in the eigen energies. So, and what is inside the square root is called the discriminant. When the discriminant is negative, then we can see that the eigenenergies would be complex. And while varying the parameter, when the discriminant becomes exactly 0, then we see that point is the exceptional point. That is the usual definition of exceptional point, right? Okay. Now I come to our simple hydrogen molecule model. Hydrogen molecule has two hydrogen atoms, and it has only 1 electrons. So overall it has 2 electrons, and total number of electrons will be conserved, that is 2 electrons. So, and they could, and the electrons can, because electrons are not fixed things, it's a quantum mechanical thing, so that electron cannot stay on one particular atom. So in the molecule it can hop from one atom to another atom. Okay. So there could be overlap between the atoms, and that's how the molecule forms. That's the binding of the 2 atoms. Okay. And so this can be modeled like in this way. So this is very similar to tight binding model, which also derived from the condensed matter, but instead of typical lattice sites, here the number of sites are 2. So it's a 2-site model, one can say. So the first atom could be thought like a one site, and the second site. So the first term is just the energy levels. We think so they are initially degenerate energy levels. So we call this epsilon. And the next term is called the hopping term. And this allows electrons to move from one side to another side. So that is a mixing term or the hopping term. And in our case, I will add some interaction between these 2 electrons as well. So just imagine what kind of states an atom can have. So one could have that state where this atom doesn't have any electron at all. So both electrons move to the second atom. Then could be there is an electron with up spin. Then could be there's a 1 electron with down spin, and there could be 2 electrons with opposite spin, respecting the Pauli exclusion principle. Okay. And the interaction we are going to use is the Hubbard interaction, and this has this kind of form. Okay. So these possible states could be written in this way, using the typical creation or annihilation operators. So these states are all the possible 6 states, because the for finite number of electrons or the atoms. And using this 6 states, we can actually construct a matrix Hamiltonian. So what we calculate in this matrix Hamiltonian, we just calculate the expectation value of between all the states. So I and J are all the possible states. These states are called also the basis states. So we can construct the Hamiltonian. Then we notice that this Hamiltonian can be actually does have a block diagonal form. So this block diagonal form can be actually categorized in 3 sectors. With one with the spin Sz equal to 1, means there's a 2 up spin electrons are there, and then Sz equal to 0, there's 1 up spin and another 1 down spin. Then Sz equal to -1, then the 2 down spin. So that's one can actually write in a block diagonal form, and this will have only one single element, so it can be easily diagonalized. This also can be easily diagonalized. This has to be done analytically or numerically. So this is little tedious. So this is the Sz equal to 0 part of the Hamiltonian. Okay, the non-trivial one. And this for the non-Hermitian, one can see that this is the characteristic equation or the eigenvalue equation. And one solving the eigenvalue equation, one can see there's a the eigenenergies could be the 2 epsilon with degeneration 4, and other eigenenergies will be 2 epsilon minus t and 2 epsilon plus t. So these all are real eigenvalues for now. Now, the first way we want to try to introduce non-hermiticity through a dissipative or current-like term. So that means we add a term which has so earlier we had symmetric term. We had if we look at this Hamiltonian, then you can see this has a plus sign in between. Now we make it little asymmetric. So this means the probability of the chance of electron hopping from left to right and right to left are the same. So symmetric. Now we introduce some kind of asymmetry. So it's not now same from left to right or right to left. So it's some kind of bias. So now if we club this together, then we can actually rewrite this Hamiltonian with T plus and T minus, which are not equal in the non-Hermitian case. And T plus is T plus lambda, T minus lambda. So one can check this. These are PT symmetric. I'm not going to this now, unless somebody asks. Okay, so and then we can rewrite this Hamiltonian, and then we get this characteristic equation. Now we can see that in the eigenenergies, there are two eigenenergies which comes very similar to the two-level system with a square root term in the eigenenergy. And we, as we said, that when this discriminant becomes negative, then we can see complex eigenenergies will emerge, right? So for this case, when this lambda, the magnitude of lambda becomes greater than T, then the eigenenergy will become complex. Okay. So this is also very simple plots to show that exceptional point. So for example, when T equal to, so we saw this, when this lambda becomes equal to T, then we should see that there this becomes 0. So also this discriminant becomes 0. So that is the onset of the, that's the location of the exceptional point. So when this lambda equal to T is 1, so when a lambda equal to -1 or +1, we can see that's that is the point where the imaginary part of the eigenenergy becomes finite, and also at the same time the real part becomes 0. This is also known. Let me see that. Okay, now we want to introduce this interaction term, this Himadri interaction term, and what it does, it just modifies this energy, and so this U terms enters into this discriminant. Also, there's an additional U terms comes out of the discriminant. So that makes a shift in the position of the exceptional point. So that is what you actually see. It's no longer actually, so earlier also when lambda becomes 1, that times and the exceptional point arises, but now it gets shifted by depending on the value of the interaction. So that is we also plot against sorry, what happened? So that is what we plot when there's no interaction. So the PT, so exceptional points actually makes the boundary between PT broken and unbroken. When it becomes complex, it's a PT broken phase. So exceptional points arises at this lambda equal to 1, then it gets shifted. So the information we get that we can easily control the position of the exceptional point by just tuning this interaction. So that is the that is one role of interaction in any kind of PT symmetric mode. Okay, so now, so actually I forgot to show, I think I didn't show the Hamiltonian. So if we so in this Hamiltonian, actually in this example, actually the Hamiltonian, this T comes because we modified in the part of the T. So there are two parts in the Hamiltonian, if you remember. So original Hamiltonian, so there's a two parts. So this first part was the energy levels, and the second part is the hopping. So what I did, I made some change in the hopping part. Okay, so and this term actually, because this is a mixing between two operators, so this comes on the off diagonal part. Now what we want to do, we do some mixing in the some change in the diagonal part. Sorry. So what we do, so that means we do some change in the orbitals. So we made this like in the two-level system, we have shown that we add some plus I gamma and minus gamma, like a gain and loss terms to the diagonal part. So then the most generic Hamiltonian becomes like this. So now my epsilons also have some kind of non-hermiticity, and that T also, hopping also has some kind of non-hermiticity. So one can also check that these are PT symmetric, and the characteristic equation becomes now a little bit complicated. So which I can simplify it in this kind of cubic equation form. We can, so sorry. So this cubic equation form, we can see that there are some terms which involves u. So like this term has u and this term has u. Now when we make u equal to 0, this L becomes 0, and then we can see the cubic equation becomes a quadratic equation. And we know the quadratic equation comes where? In the two-level system Hamiltonian, right? So I'll come to explain that. So now we just look at the evolution, look at how the where we see that what kind of exceptional point we see there. So the first case we try to study is that we fix the gamma part. So gamma was the non-hermiticity introduced in the orbital energies, right, on the diagonal term, and the lambda is the non-hermiticity on the off diagonal part. So we fix the gamma, the the diagonal part, diagonal non-hermiticity, and then vary the off diagonal one. So so here we see, so we can see, so there are actually 3 pairs of exceptional points arises. So in one case this becomes, so this is the imaginary part of the eigenenergy. So this is the first time when starts, so when the imaginary part of the eigenenergy starts becoming finite, again it becomes 0, again another point it starts becoming finite. Okay, so in that sense there are 3 exceptional points arise. Okay, and there's also another thing we noticed, that earlier we had some kind of mirror symmetry in the real part. So what we see on the, so like this, so there's an average energy in the real part, and on the top and the bottom we see it's a symmetry, there's a mirror symmetry around that, but that doesn't happen in this case. So we'll see that. Let's see. So what I was trying to say, so here we have a mirror symmetry around this value 2, right? So if we just reflect around this thing, so the blue one and red one becomes the same, so that symmetry gets broken. So yeah, now what I'll try to argue that this is the specific, so the symmetry breaks because of the presence of the interaction. So this becomes more clear when I plot against gamma, so that is the diagonal non-hermiticity, keeping the lambda fixed, the off diagonal one. Okay, so if you look at the real part, we can see that again there's a lack of symmetry in the real part of the eigenenergy, but the moment I make u equal to 0, we get back this two-level system kind of symmetric real part of eigenenergies. And how can I explain? Because as I mentioned before, when I make equal to 0, we no longer have a quadratic equation. We will no longer have a cubic equation. The cubic equation dissolves into a quadratic equation, and then we see then we see our typical or usual this two-level system kind of symmetric exceptional points in the real part of the eigenenergy spectrum. Okay, so that's that makes a difference in the exceptional point. Now we just look at try to plot how this position of this exceptional point changes with the interaction. Now in absence, so we plot this gamma against u, keeping lambda fixed. So for lambda equal to 0 case, we get this gamma to be 1 when there's a no interaction. And this has been recently also found in a similar study by this group in 2020. Okay. So that so our study also agrees with their model. But what they didn't do, that they didn't study the effect of off diagonal non-hermiticity. So once we turn on this off diagonal non-hermiticity when lambda is finite, then we see that this boundary actually depreciates. So its boundary actually reduces. So like this, the presence of this finite lambda actually, or the off diagonal non-hermiticity actually decreases or the shrinks the PT breaking boundary. So that's our observations. Okay. Now you may remember that we have marked 3 kinds of exceptional points, because there's a one. Yeah. So there are 3 kinds of exceptional points we marked, and we just want to study how they behave with the interaction, right? So in one case, the first kind of exceptional point, this lambda E1, always arises even there's no U or no interaction. So it's always arises when interaction is 0, like this becomes 1, as I mentioned in the previous slide. And for different gamma, it varies. And also this also decreases with the interaction. So but in the other 2 exceptional points, they actually don't exist or don't arise when there are no interaction. So only their finite interaction actually sets on this 2 kind of exceptional points, and that also depends on the value of the gamma. So for gamma equal to 0.1, the exceptional point array is between 1 and 2, and for gamma equal to 0.2, the exceptional point arises between 2 and 3. Okay, so that varies. However, the other third exceptional point that also arises for finite U, but the change was not that much significant, or the dependence on the gamma parameter is not that much significant. They more or less arise on the same value. So that is our observation. And so that actually distinguish 2 kinds of exception point. That the one kind of exception one is we say they are self-generated, that doesn't wait for you to be there, and the other kind of exceptional points actually arises from the interaction. So we call them interaction generated. So these are the 2 kinds of exceptional points we actually mark, and their nature also their natures are also different, because in one case the exception point actually they actually decreases as we increase the interaction strength, and in the other case the exceptional point position actually increases when we increase the interaction strength. So definitely they are different, and that this kind of 2 distinguishable feature just arises from a simple effectively 2-level system model, and having a very simple kind of interaction, which is a Hubbard interaction term. And what we just did, we just played with 2 kinds of non-hermiticity. One is diagonal and off diagonal. So that is just our discovery, and yeah, that is our key findings. So now we can, so as I can summarize or look for the future, is that this model is basically a 2-side Hamiltonian or Hubbard Hamiltonian in condensed matter language, and so that Hamiltonian has only this Hamiltonian incorporates both diagonal and off diagonal non-Hermitian parameters, the generic Hamiltonian. Now And now interaction offers a role to tune this PT phase boundary that we have observed, and also observe that interaction generates some additional exceptional points which behave different from our conventional exception points. Okay, and so in realistic Hubbard model, molecule non-Hermitian loss chain terms might be introduced through laser induced molecular ionization and dissociation techniques. So there are some experimental papers. I forgot to mention the references here. And also one can try to emulate this two-side Hubbard model, because the ultra cold atoms, ultra cold system is now easily can create a lattice models also that can be used to create a two-side model as well. And also this kind of model also can be recently created, I think, yeah, via this NMR, nuclear magnetic resonance, also can be created this kind of model. Okay, and what we are looking for the future, that we would like to extend this to really lattice model, which could be very tedious or maybe challenging, but that is we are looking onto. So, and we did something similar in our yeah, maybe 6 years to 4 years ago in the Hubbard model. We can try to incorporate that in this kind of non-Harvard CJ. Yeah. So this has been okay. This has been submitted for review, and codes are available on GitHub. So anybody can download and check the codes, and can look at the paper. And right now, I think my contract has finished in Hangzhou, so I'm looking for opportunities or collaboration. So if anybody is interested, can contact me. And I would like to thanks the organizers for giving me an opportunity, and my friend Frank Onanga for telling me about this virtual series is going on. And the place where actually I met the students, that is called Homi Bhabha Center for Science Education, which is situated in Mumbai, India. So thanks for a kind attention.
Thank you very much, Himadri. Thank you.
Yeah.
Any questions, any comments?
But this is a very simple model, so I don't know, it's not very advanced. But I think this there's some kind of rich physics I got. We just need to.
Maybe people are tired now as well.
Yeah.
If there are no questions, then let's thank Himadri again. Thank you very much.
Okay. Thanks.